In this video, I want to show you how you can identify a substance as an ionic solid, a molecular solid, or even atomic solid such as a group 8 solid or metallic solid or even a network covalent solid. So ionic solids composed of ions. And a good way to identify it is to see if you have a substance that is composed of a metal and a nonmetal, like sodium chloride. Sodium is a metal, chlorine is a nonmetal. Some other examples include magnesium oxide and ammonium chloride. Now, ammonium chloride doesn't have any metals in it, so this is one of those exceptions. However, it is composed of ions. Ammonium is a polyatomic ion, and chloride is an ion. So that's how you can identify an ionic solid. Typically, it contains a metal and a nonmetal, but it's composed of ions, which are particles with positive and negative charges. Ionic solids, for the most part, have relatively high melting points. The melting point for sodium chloride is, let's see if I can put it in a different color, 646 Celsius. For magnesium oxide, it's a lot higher. It's like 2,852. So some ionic solids have very high melting points, others relatively average, but ionic compounds with very high charges tend to have higher melting points. For example, magnesium has a positive 2 charge, but sodium has a plus 1 charge. And so due to the high charge on magnesium, that's why it has a higher melting point. Now, there's a term that you need to be familiar with when dealing with ionic solids, and that is lattice energy. Magnesium oxide has a much higher lattice energy than sodium chloride, and that's one reason why it has such a high melting point. Lattice energy increases with increase in charge. So if you increase the charge on an ionic compound, the lattice energy will increase, and typically the melting point is higher. The second thing is size. If you can increase the atomic radius of an atom, the lattice energy decreases, and as a result, the melting point decreases. So ionic compounds with very high melting points tend to have small ions with high charges. Now, the next category are molecular solids. And for the most part, compared to ionic solids and metallic solids, molecular solids have very low melting points. Carbon dioxide, for instance, has a melting point of negative 56 degrees Celsius. Water melts at 0 degrees Celsius. Now, a good way to identify a molecular solid is, for the most part, it's composed of nonmetals. It's composed of molecules as opposed to ions. And these molecules tend to be small. Some other examples include fluorine, chlorine, bromine, and iodine. Now, when comparing molecular solids let's say, in the same column or group in the periodic table, the melting point will increase as you go down a group. Iodine, for example, has a relatively high melting point compared to fluorine because it has a higher molecular weight and it has more electrons, so therefore it has more London dispersion forces. The melting point of fluorine is negative 219.7 degrees Celsius. For chlorine, it's negative 101.5. Bromine is negative 7.2. And iodine is 113.7. So as you can see, as you go down a group, the melting point will increase due to the fact that iodine has more LDF forces or van der Waals forces. Fluorine is a gas at room temperature. Chlorine is a gas. Bromine is a liquid. Iodine is a solid. So if you know the physical states of the compounds or molecules you're dealing with, solids usually have higher melting points than liquids or gases. So if you know a substance to be a solid and another one is a gas at room temperature, the solid is for the most part going to have a higher melting point than the gas. Now let's move on to atomic solids. Now there's 3 different categories that you need to be familiar with for atomic solids. So these include Group 8A atomic solids, that is the noble gases. and then you have the metallic solids, and then the network covalent solids. So as we said before, ionic solids are composed of ions. Molecular solids are composed of molecules. And atomic solids are composed of atoms. Now sometimes you may have like giant molecules as well, but we'll talk about that later. For the most part, these are made up of atoms. So let's talk about the group 8A atomic solids first. So these include like neon, argon, krypton, and so forth. Now, group 8A atomic solids have very low melting points. The melting point for neon is extremely low. It's negative 249 degrees Celsius, even lower than most molecular solids. Argon is negative 189, krypton is negative 157, and xenon is negative 112. But notice that the trend is the same for the halogens. As you go down a group, the melting point increases, as in the case of molecular solids. And the same is true for group 8A solids. Krypton has a higher melting point than neon. So that's another trend you want to keep in mind. Next, we have the metallic solids, which the melting points can vary greatly. So zinc has a relatively average melting point. The melting point of zinc is 420 degrees Celsius. Mercury is a liquid at room temperature. It's a liquid metal, and so it has a very low melting point of negative 38.8 Celsius. Tungsten has a very high melting point, and that's like 3,422. So as you can see, for metals, the melting points can vary. Now you want to be familiar with the metals that have very low melting points, because the rest, for the most part, are usually high. Gallium is one of those metals that have a low melting point. It's about 30 Celsius. In fact, you can hold a solid chunk of gallium in your hand, and the heat from your hand is enough to melt it into a liquid. Cesium is another metal with a low melting point. The melting point is 28.5. Copper has a melting point of 1,085. So the melting points for metals varies a great deal. Now you need to be familiar with certain properties of metals. Metals can conduct electricity, they can conduct heat very well, and they're malleable, they can be hammered into thin sheets, and they're also ductile, they can be pulled into wires. So make sure you know those properties of metals. Molecular solids tend to be soft. Ionic solids tend to be hard but brittle. Now let's move on to the network covalent solids, also known as the network atomic solids. The first element we need to consider is carbon. Now there's two main allotropes of carbon that you need to be familiar with. There's others, but the main two are diamond and graphite. Diamond has a nice crystal clear structure, whereas graphite is black and slippery. Diamond is very hard. It's one of the hardest naturally occurring substances. It doesn't conduct electricity, it's an insulator, but it does conduct heat very well. It's an excellent thermal conductor. Graphite, on the other hand, does conduct electricity. And the melting points of these two solids, they can vary with pressure, but it's about above 3,000 Celsius. It could be 3,500, 4,000 Celsius, but it's over 3,000 Celsius. And to melt these substances, the pressure has to be very high, above normal atmospheric pressure. Another example of a network atomic solid is silicon carbide. Now this is composed of two different atoms, silicon and carbon, but it is a network covalent solid, just like carbon. It's a metalloid, it doesn't conduct electricity very well, and silicon carbide does have some thermal conductivities to it, like diamond carbon. Its melting point is pretty high. It's about 2,800 Celsius. Another network solid that you need to be familiar with is silicon dioxide, also known as quartz, and also in the form of silica. Glass is another form of silicon dioxide, and also the sand that you see in the beach. The melting point of silicon dioxide for the most part, averages around 1700 degrees Celsius. Boron nitride is also another network atomic solid, and its melting point is about 3000 Celsius. So the network atomic solids, they're composed of giant molecules. They have strong directional covalent bonding, whereas metallic solids, they have strong non-directional covalent bonding. And the electrons in atomic, or rather metallic solids, the electrons are delocalized, and that's why they can conduct electricity very well. The electrons in a metal, they can be shared among many atoms. Now, in graphite as well, the electrons in graphite, the pi electrons, are also delocalized as well. So not all of the electrons, but some of them. And that's why graphite can conduct electricity. Whereas in diamond, the electrons are localized. They're stuck to the atoms that they're attached to. And so they can't move from one atom to the next. And so diamond doesn't conduct electricity. But metals, graphite, they can conduct electricity because the electrons are free to move from one atom to the next. And so it's said that the electrons are delocalized. They're not stuck to one atom. They're free to move around from thousands of atoms. Now, how can we identify a network covalent solid? The best way to identify it is to look for elements that are close to the metalloids. If you see elements such as carbon, silicon, these are metalloids, boron, nitrogen, elements in that region like group 3, group 4, group 5 elements, if you see that, chances are it might be a network covalent solid. So here's silicon in group 4, here's carbon, and then below that is germanium, and then here you have boron, nitrogen, aluminum, phosphorus, and then this is indium and arsenic. So if you see carbon by itself, it's a network covalent solid, or silicon by itself. If you see boron paired up with nitrogen, that's going to be a network covalent solid. Even aluminum paired up with phosphorus, that can also form a network covalent solid, or even aluminum with nitrogen. So if you see elements in this vicinity, there's a good chance it can form a network covalent solid. Now let's work on some multiple choice problems to see if you remember what you've learned. Now there might be some other questions that we haven't covered in the beginning of this video, so hopefully you've studied this section. So which of the following is an ionic solid? So now recall, ionic solids are composed of ions, typically made from metals and nonmetals. A is an ionic solid. Calcium is a metal, chlorine is a nonmetal. So that solid is composed of the calcium plus 2 ion and the chloride ion. Nickel is a metallic solid. Nickel is a metal. C6H12O6, which typically can represent glucose or fructose, that is a molecular solid. It's composed of molecules. Helium is a noble gas, so that's a group 8A atomic solid. Silicon carbide, that is a network covalent solid. So A is the answer to this problem. Number 2, which of the following elements is ductile? Now feel free to try this problem if you want to. You can pause the video and select your answer. Ductility is a property of metals. Metals can be pulled into wires. Sodium fluoride, that is an ionic solid. Sodium is a metal, fluorine is a nonmetal. Argon is a group 8A atomic solid. Boron nitride is a network covalent solid. Copper is a metal, so copper can be pulled into wires. So copper is ductile. It's also malleable. It can be hammered into sheets. Diamond can't be pulled into wires. I've never seen a wire that's composed of diamond. That'd be interesting though, but that's just not a property of that substance. Number 3, which of the following substances can conduct electricity in the molten state? Is it silicon carbide, sodium bromide, xenon, water, or carbon dioxide? Water is a liquid, and water doesn't conduct electricity in the liquid state. Pure water is not an electrical conductor. However, if you add salt to water, it does conduct electricity. because you have free-flowing ions. For something to conduct electricity, you need a mobile charge carrier. In the case of metals, the electrons conduct electricity because the electrons, which have a negative charge, are free to move. In the case of salt water, the ions, which carry positive and negative charge, are free to move. They can freely flow within water, and so that's why salt water conducts electricity. So you need a mobile charge carrier for electricity to be conducted within a material. Carbon dioxide is a molecular solid, and even in the molten state, it doesn't conduct electricity. There's no free-flowing ions or free-flowing charge. Silicon carbide doesn't conduct electricity in a liquid state. Sodium bromide does conduct electricity in a liquid state. Now, it's important for you to understand that ionic solids or ionic compounds in the solid state do not conduct electricity. In the solid state, the ions are fixed in place. They're not free to move. So, ionic solids like salt is an insulator. However, if you can melt it into a liquid or into the molten state, the ions are free to move. And whenever you have free-flowing charge, they can conduct electricity. And also, in the aqueous state, when they're dissolved in water, they can conduct electricity. So just keep that in mind. Xenon is a noble gas, and in a liquid state, it doesn't conduct electricity. Number 4. Which of the following substances have the lowest melting point? Is it ionic solids, molecular solids, atomic solids? Which one is it? Molecular solids and group 8A solids or noble gases tend to have the lowest melting point. Zinc at room temperature is a solid, mercury is a liquid, neon is a gas, carbon dioxide is a gas, and magnesium oxide is a solid. So if you know the physical state of the substance, you can eliminate the ones in a solid state. Solid compounds tend to have higher melting points than liquids and gases. So we can eliminate liquid mercury. So we're between neon and carbon dioxide. Noble gases usually have lower melting points than molecular solids. The only forces acting on noble gases are London dispersion forces. Now granted, carbon dioxide is nonpolar, which does have London dispersion forces, but it does contain polar bonds. So it turns out that neon is going to have the lowest melting point. And I believe we mentioned the values for these substances. Zinc was about 420 degrees Celsius, so it's pretty high. Mercury, it's a liquid metal, and so it's negative 38.8 Celsius. So some metals have relatively low melting points. Neon is negative 249 Celsius, and carbon dioxide, it melts at negative 56 Celsius. Magnesium oxide is very high, 2,852 Celsius. So keep this in mind. Ionic solids and network covalent solids tend to have very high melting points. Metals, the melting points can vary. It can be very low or it can be very high. Like tungsten was over 3,000 degrees Celsius. Molecular solids and noble gases, those are the ones that have very low melting points. But for the most part, noble gases have extremely low melting points. Now what about number 5? Which of the following substances does not conduct electricity? Is it potassium fluoride in the liquid state, graphite, aqueous sodium hydroxide, silver, or diamond? Potassium fluoride is an ionic substance. In the liquid state, it's in a molten state. And molten ionic compounds do conduct electricity, so we can eliminate A. Graphite is a network covalent solid, and it does conduct electricity. The pi electrons are free to move. Sodium hydroxide is ionic, and it's in an aqueous state, which means it's dissolved in water. So we have free-flowing ions, and so therefore that conducts electricity. Silver is a metal, which also conducts electricity. A diamond is a network atomic solid, like graphite. However, diamond structure does not allow it to conduct electricity, and that's just something you need to know. So E is the answer for this problem.